Stepping on some hard integrals. We have this integral from 0 to 1 x ln x over x to the power 4 plus x square plus 1 dx, and we have to evaluate this answer is given here. Okay, well, let's begin. Firstly, we see that it is the perfect place for applying substitution as y equals to x square, because we have x dx over here. So applying the substitution will give us 2 times x dx, which can be replaced by dy by 2. dy by 2 equals to x dx. So now using the substitution, we have integral from 0 to 1 and ln of root y over y square plus y plus 1 and then dy over 2. Now we can just take 1 by 2 out from here. So using the property of logarithm, that the exponent of the term inside the logarithm just comes out. So if we use that property, it will be 1 by 2 over here from the square root and 1 by 2 from here. So now this is integral from 0 to 1 ln y by y square plus y plus 1 dy. Okay. Now if there was no this log term, we could have used completing square method, but for this it won't work, so we are going to use some other ways. Some of the other ways by which you can reduce this into nice expression is you can multiply numerator and denominator by 1 minus y, and in that way this will be a minus b, a square plus ab plus b square. And we know this is the formula of a cube minus b cube. So this will be 1 by 4 integral from 0 to 1 ln y 1 minus y over 1 minus y cube dy. Now we have integral. Okay, now what we can do is we can just substitute z as y cube, and then z to the power 1 by 3 equals to y. While we are doing this, is we are trying to take this into one of the standard forms of integral. You will see that wrong. Yeah, so it's 1 by 3 z to the power minus 2 by 3 dz equals to dy, and then this will be equals to into 1 by 4. This is actually 1 by 3. I can erase and write this. Okay. Yeah, it's 1 by 3. Okay, now it's 1 by 4 out, and then integral from 0 to 1 again, even if it's in the limits, and this will be ln of z to the power 1 by 3. So that's 1 by 3 ln z, and here 1 minus z to the power 1 by 3, and in the denominator we have one minus z, and dy is just 1 by 3 z to the power minus 2 by 3 dz. Okay, so now after this we can just take 1 by 9 out again, so that will be 1 by 36 times integral from 0 to 1 and ln z, and this will be z to the power minus 2 by 3 minus z to the power minus 1 by 3 by 1 minus z dz. And now after this, what we can do is now we will just distribute these two terms, and then they will be in one of the standard forms of integral, from where we can use some standard formulas. So ln z to the power minus 2 by 3 by 1 minus z minus ln z to the power minus 1 by 3 by 1 minus z dz. Now we have a relation in terms of trigamma function. Basically, first I need to introduce what a trigamma function is. Basically, digamma function, which is represented like this, it's just the derivative of log of gamma function. So d dz, derivative of log of gamma function. So this should be something like derivative of gamma function by gamma function. And we do have other representations for gamma function, digamma function too. And the other representation is one of the other useful representations like this. Digamma function of z plus 1 is equals to a negative of Euler-Mascheroni constant plus integral from 0 to 1 1 minus x to the power z by 1 minus x dz. Though till now we don't have any logarithm in this expression, but we can bring that out if we do integral under, if we do differentiation under integral sign. So we can do something like we can just differentiate these expressions. Sorry, this is just dx. Yeah, this is dx. Pardon me. Okay. Now we can do a differentiation on the integral sign, and then we have differentiation of gamma by dz is equals to, this is a constant, so goes to 0, integral from 0 to 1. Here 1 by 1 minus x will be constant because we are in the z world, and 1 will go to 0, and this will be minus x to the power z times ln of x dx. So now you see we have a logarithm over here, and thus we can proceed. Now derivative of gamma function was digamma function, and then now derivative of digamma function will be trigamma function, which is represented like this, z plus 1 is equals to, so negative sign comes out, and 0 to 1 x to the power z ln x by 1 minus x. So this is dx, sorry again, pardon me. So, and this is dx. So now we see that this integral is in fact a standard integral. Yeah, x to the power z ln x over 1 minus x from 0 to 1. Its negative is just derivative of trigamma function evaluated at z plus 1. So since this is a standard integral, we can use it here. Here we have the same form. Here we have, instead of x we have z, instead of z we have these constants. So now we can evaluate them. Okay, so we will just write these integrals again. The integral we had was 1 by 36, and the integral from 0 to 1, and it was 0 to 1. Yeah, it was z1, and ln z to the power minus 2 by 3 1 minus z dz, and then it was negative sign, integral from 0 to 1 ln z to the power minus 1 by 3 by 1 minus z dz. Now since this is in the standard form, we can use the trigamma function, over here. And sorry, this is just a tri-gamma function of okay, this is just tri-gamma function of minus 2 by 3 plus 1. I don't know why this is happening. So this is just tri-gamma function of minus 2 by 3 plus 1. Yeah, no, minus, again we need this negative sign as well, since we don't have a negative one over here. So it is just negative of minus 2 by 3 plus 1, and here a negative negative becomes plus, and this is tri-gamma function of minus 1 by 3. Yeah, or z is minus 1 by 3 over here, minus 1 by 3 and plus 1. Yeah, so the main idea behind solving this problem was just knowing that this form is a standard integral, and its integral is negative of a tri-gamma of z plus 1. So this was the main concept in this integral. And now our solution is 1 by 36, tri-gamma function of 2 by 3 minus tri-gamma function of 1 by 3. So now you can evaluate this using some Wolfram alpha like calculators, and that's it. This is the answer. Thanks for watching the video.